In this video, we'll be looking at the BC topic known as Euler's method. This is always on the BC exam, usually in the calculator section, but also it's part of the free response occasionally. So let's start by getting just a general idea of what Euler's method is used for. You use Euler's method when you want to find a numerical solution to a differential equation when you have some initial value. So let's look at this first graphically. So first of all, this blue graph that they've got sketched is, let's say, our actual function f of x, or y equals some function. Now remember, we normally have with differential equations like dy dx would be something like 2x plus 5. So what we do is we use the derivative and the slope of the tangent line to get us an approximation for various points. So let's say that this was at x equals 1, and I might want to know what's happening over here at x equals 1.3. So what I would do is I would use an approximation to find 1.1, and then an approximation to find 1.2, and then when I get finished, I would have an approximation for 1.3. Now you do need to notice that you do have just an approximation because the actual value for 1.3 would be on the blue curve. And the farther away from the initial point that we get, the more error we're going to have in our approximation. So if you look out here, and let's say that was 1.5, notice that there's a large error there between the actual value and our approximation. So notice that they make the note that the approximation gets less accurate the further away you are from the initial value. Also, if you want a better approximation, you'd want to put your values close to each other. So if I wanted to know like 1.3, I would really like to do maybe something closer to 1.3 as an initial value, but I want to keep my what we call the step very small. So in this case, we're using a step of 0.1. It would be nice if we could do smaller than that, but then that's going to take a lot of time to do. Also, this is important that they give you this AP tip because you are often asked this question. It says if your approximation is, or if your function is concave down, then your approximation is going to be above the actual curve. And if your curve is concave up, then you're going to be below, which is the case here. So a lot of times they'll ask you after you've used Euler's method, is this an over approximation or an under approximation? Well, if you're concave up, it's an under approximation. If you be concave down, if your graph is concave down, you'd have an over approximation. So now let's take a few minutes and actually work through a couple Euler's method problems. A lot of times you're going to need a calculator to compute these values. They don't necessarily try to make them turn out nice for you. So what I want to do is I want to find f of 2.3. I'm given that my slope, dy dx, is 2xy, and I know the initial condition of f of 2 is 4. They also tell me that I'm going to use a step of 0.1, which is always my dx or delta x. So here's what we do. You want to make a table, and I always do these in tables, and you want to label the table with 5 columns. You want to have x, y, dy dx, dx, and then dy. Now, one thing that's really important is that these last 3 columns, if you take dy dx and multiply by dx, you get dy, which is going to be important when I go through the actual computations for this. So let's start with, I've already filled in the first numbers in my table. They told me my initial condition of 2, 4. So x was 2, y was 4. And now I use my slope, or my differential equation to find the slope. So dy dx is 2 times x times y, which would be 16. My dx is my step, my delta x, which is 0.1. Now to get dy, I take dy dx times dx, and that gives me 1.6. Now remember that dx stands for delta x, and dy stands for delta y. So what I do now is I go back to my original x and y. This x was 2, and I'm going to adjust by my dx, my delta x, which is 0.1, which now means that my new x is 2.1. My y was 4, but my delta y was 1.6. So I now increase that. That's how much my change in y is, by 1.6. So that's going to put me at 5.6. I took 4 plus 1.6. Now I use this x and y in my equation that dy dx is 2 times xy, and I get a new dy dx. So I take 2 times 2.1 times 5.6, and I get 23.52. My delta x stays the same, it's 0.1. So then now I multiply dy dx times dx to get dy, and that gives me 2.352. Now, there's my delta x and my delta y. So I want to adjust my x's and y's. So this goes up to 2.2, and then I take 5.6 and I add 2.352, and I get 7.952. Now I use those numbers to get my dy dx again. So I take 2 times x, which is 2.2, times y, which is 7.952, and I get 34.9888. dx is 0.1, so I multiply dy dx times dx, and I get 3.49888. And now we're going to adjust our x's and y's. This is 2.3, and I take 7.952, and I add 3.49888, and I get 11.4508. And I can stop here because I now know, remember the problem was find f of 2.3. When x is 2.3, y is 11.45088. And in 3 decimal places on the AP test, we would expect that they would accept either 11.450 or 11.451. So let's look at one more example of Eulers' method. This time we want to find f of 1.4. We're given that dy dx is x plus y, and the f of 2 is 8. Now notice that in this case, I am actually decreasing because I'm going from f of 2 back to f of 1.4. So my delta x, even though it's 0.2, it's actually going to end up being negative. So I want to keep that in mind because I'm decreasing. So then dy dx, using my first point of 2 and 8, dy dx is x plus y. Well, that would make that 10. Multiply by negative 0.2, and I'm going to get negative 2. And then I'm going to adjust my x's and y's. So 2, delta x is negative 0.2, so that's going to put me at 1.8. My y was 8, but my delta y was negative 2, so that moves it to 6. Now, dy dx, I take x plus y, 1.8 plus 6 is 7.8. dx is negative 0.2, and I get negative 1.56. So again, I adjust everything. The 1.8 is going to decrease by negative 0.2, so it's down to 1.6. And then I'm going to take 6 minus 1.56 and get 4.44. To get dy dx, I add that y, 4.44, plus my x, 1.6, and get 6.04. Negative 0.2 is my dx, and I'm going to get negative 1.208. Decrease my x's again by negative 0.2. I'm at 1.4, and then take 4.44 and subtract 1.208, and I'm at 3.232. And again, I can stop because I wanted f of 1.4. I'm at 1.4 and there's the y value. So my approximation for f of 1.4 is that it's 3.232. Euler's method is actually very easy to follow. You just need to memorize how to set up your table. And always do these in table form. They're the easiest way to work through them. And like I said, this is usually on the multiple choice test or part of the test. Sometimes they'll have it on the free response as part of a slope field or a differential equation problem. They have had these on the non-calculator part, but they usually only ask you to do 1 or 2 steps, and they have very nice step values to decrease by, so they're easy to work without a calculator.